seen in the last lecture. So we finally got the machinery that's needed to compute scattering amplitudes in quantum field theories. So in particular, we looked at nucleon scattering. So two nucleons scattering into two other nucleons. And we computed this S matrix. And we computed a leading order, which was order g squared. And we got the following result. Times by P2 prime minus P. Okay. Good. So a couple of things to say about this. Firstly, there's these plus I epsilons that sit on the bottom here, because this was the definition of the Feynman propagator. But notice that by the time we've got to this expression, we're not integrating over anything here anymore. And actually, what sits on the bottom is never going to diverge. Okay? So it's never going to be 0, so the whole thing's never going to diverge. So we can just cross these things out. We don't need those plus I epsilons anymore. Epsilon was always to be thought of as something which was infinitesimally small. So they just vanish. That's typically true for any tree-level amplitude you want to write down. It's not true for loop integrals. When you do loop integrals, you'll typically still have to integrate over some momentum, and you've got to keep those I epsilons in. Okay? But for tree-level amplitude, you can usually just forget about. We'll compute lots of amplitudes of this type, and they all come with a factor of 2 pi to the 4 times the delta function, which just tells you that, that the sum of the incoming and outgoing momenta is conserved. So in writing down the amplitude, we'll just define this bit and this bit to be the amplitude and just remove this. Okay? So we'll define the amplitude by stripping off this momentum. So in general, some initial state going to some final state is always going to have a 2 pi to the 4 times some delta function where this is the sum of the final momenta. And this is the sum of the initial momenta. Okay, and it's this thing here that we're going to call the amplitude. AFI. There's a factor of I here. This factor of I is in some sense purely conventions, but it's there so that this amplitude agrees with similar things you would compute in scattering theory of non-relativistic quantum mechanics, which you've done already. Okay.
Are pure particle states normalizable?
So say again, are pure?
Like a pure momentum state in non-relativistic quantum mechanics would be not actually part of the fluid space. Is the same thing true with?
Yeah, exactly the same.
Okay, so this is if you integrate over several momenta, which is what you have to do for things to make sense, then the right-hand side makes sense as well. And you get
yeah, good. Okay. So I'm going to come to that question. Actually, I'm going to duck that question later in the lecture. So let me wait. then I'll duck it. Okay, so this is in general what we mean by the amplitude. Your homework this week is just going to be to compute a whole bunch of amplitudes of this type in this theory, and I think maybe apply to the fourth theory as well, which we'll introduce in this case. Let me just give some examples. You know, once you've got the Feynman rules, it's really dead easy just to write these things down. In the homework, I think for a couple of them, you're going to have to go through Wick's theorem and just convince yourself that the Feynman rules give what they're supposed to give. So other
sigma
so we could consider nucleon antinucleon scattering goes to two mesons. What are the diagrams for that? Two diagrams. These are the mesons, these are the nucleons. This is the nucleon, this is the anti-nucleon, which you can tell because the arrows are going the opposite way. So this is psi and this is psi bar in both of these. Okay. So what's the amplitude for this? Well, we just use that Feynman rules. There's two vertices, so it's goes as g squared. And now the only real difference between what we had before is that the propagator that you have in the middle here is the propagator for the nucleon instead of the propagator for the meson. So there's a capital M at the bottom instead of a little. Another process is meson scattering. Two mesons goes to two mesons. The kind of diagrams we can draw for this are a little more complicated now. So we have two mesons coming in and two mesons going out. So who can think of what the simplest diagram we can draw is that connects two mesons to two mesons, other than just connecting the lines? Nima, crossing. You mean like this? Yeah, but there's no vertex here, so that really means it's going up and over, and that's the same diagram. It's just nothing happening. In a different theory where there would be a 5-4 term, then that would actually be a vertex where you'd have to put in an interaction. But in this theory, the mesons don't couple directly to the mesons. The only vertex we have to play with is like this, a meson coupling to two. Yeah.
Didn't you have like a meson with a loop?
Yeah, good. So this is the kind of interaction that we have to write down. So for meson scattering, mesons to two mesons, there's no true level diagram. The first correction comes with, the first contribution comes with. To write down the amplitude for this, I can just use the Feynman rules again. But I have to be a little more careful. Remember, this momentum is coming in, and this momentum is coming out. And then I'm going to have to pick an arbitrary momentum on one of these sides. So let me just pick this side. So let me say there's a momentum k running here, but then I've got delta functions at each of the places. So the delta functions dictate where the momentum are on the other sides. So in particular here, we've got a k minus p2 prime, because p2 prime went out that way. Here we've got a k plus p1 prime minus p1. And here we've got a k plus p1 prime. Okay. And the reasons these are the same are because the sum of all momenta is equal to 0. Sorry, that's kind of squeezed down the bottom here, but basically it's a product of 4 factors. Each of the factors is the momentum squared minus the capital M squared plus I epsilon, and they're all multiplied together. Okay. Yeah. Can I?
No, I don't know. What if we had assigned arbitrary momenta to each one of those inner internal lines, and then wouldn't the delta functions take care of momentum has to be conserved along the vertices?
Yeah, but then you'll be integrating over 4 different momenta with a bunch of delta functions.
Yeah.
And you'll do those integrations using the delta functions, and you'll get x.
Right, but that's like the formulaic algorithmic way to do it is just to do that, right? Like A1 and A2.
Yeah.
So you've skipped steps.
So I've skipped.
Okay, you're not just
Yeah.
doing it. I was just wondering.
Yeah.
But if you did this computation the way, without skipping steps, you would have 4 delta functions, and then you integrate only 3 times to get to 3 delta. So you should get a delta function in the end.
Yeah, the delta function that gets at the end would be the sum of all of them equals 0. Would be the overall delta function, and that's what we've stripped off when writing down this amplitude. So the actual f s minus 1I comes with the delta function, but I've just removed it.
Okay.
Yeah.
Why is there only one diagram now? Why don't you have to swap? Running back and get in there. Why don't you have to go to one?
Ah, good. So do we? Let me see. I think you're absolutely right. Yeah. Plus. Okay, so you can see that when you do these one-loop integrals, or one-loop diagrams, you're left with an integral. And it looks pretty nasty, right? It doesn't look like it's obvious how to do it. This integral, at least, is going to converge. You notice that these integrals, you usually have problems at high momentum. That means that when the k gets large. So you basically got to be 4k here, but you've got 8 powers of k squared on the bottom. So it's an integral of d4k over k to the 8, and that converges. Okay, so we're at least good there. But you've still got to do the integral. And there are techniques to do these integrals that you'll learn. I'm not sure which course, but I'm sure at some time over the next few months you'll learn how to do these kind of integrals. Okay, a good rule of thumb is that if you have to do a one-loop integral, you should just be able to sit down and do it. You know, it might not be the nicest thing in the world, but in any theory you have, you shouldn't be afraid to just sit down and do one-loop integrals if necessary, like this. Two-loop integrals, you know, if you come across these in your research, you really have to have a very good reason to sit down and compute them, because it's going to take you a long time and be very painful. And anything more than that, you know, you typically leave to experts who just compute these integrals for a living. Okay. Nima. This is the leading order contribution to this process. It's order g to the 4, so it's a more suppressed process than this.
What I mean is that, is it possible for one of them to do nothing, absolutely nothing, and the other just decay into 2
nucleons, and then. Ah, I see. Good. It's a good question. You're interested in this, yeah. So these diagrams are there, and I've been subtly avoiding talking about them. What's really happening here is that when a meson moves along in space, it's continually doing this. And when you compute the corrections to this, you'll find that it's infinite. You have to work out how to deal with that. And there's a very nice physical meaning for what's happening here. What's going on is that the meson's moving and constantly splitting into a nucleon and anti-nucleon pair and combining and moving. And that's changing what you observe as the mass of the meson. So this is all to do with this story of renormalization. But the little m that we've been putting in the Lagrangian, which appears to give you the mass, is not the actual mass that you will observe that meson. What you have to do is you have to take into account diagrams like that mass gets shifted, and then everything we've said carries on. But this is really the topic of the next quantum field. So these diagrams are there, but they do something a little bit different that's to do with renormalization.
So should you include those diagrams when writing down these amplitudes?
No, what it will do is change what you mean by this capital M. Actually, not this one. This will change what you mean by little m.
So you throw it away. You forget about those diagrams and change m.
Yeah. So there's actually you can make this a little more formal, and I think this will be part of the tutorial session tomorrow, maybe. But the kinds of diagrams you should consider are called connected diagrams, and it's what they sound like. It's where everything is involved in the process. So this is a connected diagram because all the external lines are connected, whereas this one isn't. So there are some caveats to what I've been saying that will be covered in due course. Where due course is not this course. Okay. Are there any other questions about this? No? All good? Okay. I should say that in the last couple of years, or maybe a little more, there's been lots of progress in understanding how to compute these integrals of this type. Not so much in just scalar theories, but in gauge theories, which, if you don't know what they are, you'll come across them even at the end of this course. But theories with spin 1 particles interacting, and also in gravitational theories as well. And it sounds like it's going to be really dull, right, sitting down and computing integrals. But what's amazing is that in certain theories, people do these horrendous calculations, and what comes out is something very, very simple and elegant at the end. Yeah, so there's various different approaches to this. Some people just sit down and calculate with brute force. Other people, like Freddy Cacciazzo here, together with Nima, are using twisters. Yeah, so what it means if you're doing a horrible calculation and getting a beautiful answer for a reason that you don't know is that you've missed something. You know, that there's some important ingredient that means the whole calculation should have been elegant and beautiful from the beginning, and there's something you don't understand. So there is a big research program led by people like Nima and Freddy and Lance Dixon on the West Coast and various others, trying to understand not these particular integrals, but actually I think what they do is they take hard integrals and reduce them to this one. But you know, there's some hidden structure inside this perturbation series that isn't really apparent and that people still don't fully understand. So it's an interesting area of research. Okay. Good. Let me just tell you about a different theory. This is universally called phi to the 4 theory, or sometimes lambda phi to the 4 theory. It's just a single real scalar field. with a marginal, I think I probably want, with a marginal coupling. Marginal means that this is a dimensionless number. Okay, so you just take lambda to be much less than 1, and now you've got a weakly coupled theory that you can start to compute. Okay, so we've just got this interaction. What's the vertex that we now write down when we're doing Feynman rules? It's this. Okay, so now these guys actually hit each other, and this is the vertex you use to join diagrams together, not the trivalent vertex that we had in the previous guy. Okay, 4 legs because it's phi to the 4. Yeah.
If you included the previous interaction
Terms, could you have both types of vertices?
Absolutely, yeah. So if you had a phi to the 4 and that scaling Yukawa, you would start having more complicated diagrams.
Why not phi to the 3?
Yeah, we could have phi cubed. The problem is that phi cubed looks like this. Now, the energy, the potential energy is, this is minus the potential energy. So the potential energy is this plus this. If you've got phi cubed, it's a theory whose energy is unbounded below, because it can just run up. I should say that the same problem is actually there in the scalar Yukawa theory, but it turns out if you plot that potential, the origin is a minima, but not a global minima. So if you move far enough away in the phi direction, it's also true here because it's m squared, then you can roll off to minus infinity. So it's a real issue for that scalar Yukawa theory as well. And what it means is that, what I've been looking at is small perturbations around the origin, if you like. And I can't push those perturbations too far, otherwise the theory is going to run somewhere basically beyond. By the way, you ask any cosmologists, they're actually people you live somewhere like this. They'll think about our potential. There's some scalar field in the universe, and when we sit in some minimum, we're called a global minimum, and we're just 14 billion years away from tunneling through somewhere and all dying. That's, I think, what most cosmologists would. Most very theoretically inclined cosmologists are. The reason is that we live in a de Sitter space with a positive cosmological constant, but any theory you write down typically has possibilities for zero or negative cosmological constants. We just have to tunnel through them. I'm not sure I can.
Just to go back a little bit, I'm having a little bit from why does a phi to the 4th correspond to a 4-valent interaction?
So let me tell you what the Feynman rule is for this, and then explain why that's the Feynman rule, and at the same time we'll see why this is needed. Are there any other questions? Okay, so the Feynman rule for this is, remember, whenever you see a vertex, you have to associate a number to the vertex. The number is minus I. That was the same as we had before, times lambda. Now, this is a little different from what we had before because of this 4 factorial. Why is it lambda and not lambda over 4 factorial? So let me now explain that, and in doing so, I'll also explain why we've got these four guys there. Okay, so remember what's going on here. This is the interaction part of the Hamiltonian. And that means that when we're doing Dyson's formula, we're getting, we're sandwiching products of this interaction Hamiltonian between initial and final states and time ordering them. Okay. So, what's the right way to say this? So let's look at phi to phi scattering in this. In this particular theory. So we've got some initial state, some final state out here. There's a 1 over lambda factorial, p1 prime, p2 prime. And what's going to happen is there'll be some there's a factor of the interaction Hamiltonian, so that's phi to the 4, and it's going to be time ordered, and then we're going to use Wick's theorem and change that time ordering into normal ordering and pick up some propagators. Okay. So we're going to get after Wick's theorem things like this. Okay. Now the reason there's 4 guys here is basically because there's 4 guys here. And so what's going to happen in this case? Each of these has an A and an A dagger sitting in it. And so what we want to do is take an A from 2 of these and kill these, and then an A dagger from the other 2 to build up these, and then we'll get something non-zero. Okay? So that's what this picture is capturing for us, the fact that sort of this theory can take 2 mesons and kill them, and then produce another 2. Okay? And typically that's always going to be the case. You have some polynomial of fields sitting here, and you just count the number of each field that arises, and that's the number of legs on the vertex that's allowed. This also tells us what happens to this 4 factorial. Notice that the way of picking the 2 that are going to kill this and the 2 that are going to hit this is 4 factorial. So there's 4 factorial different ways of killing these and producing these. That cancels this 4 factorial, which is why we just have a lambda here and not a lambda over 4 factorial. Baffled looks. OK, you should maybe just sit down and compute this in phi to the 4 theory. Expand this out in A's and A daggers, and just see it for yourself. And you'll find that it comes out to be proportional to lambda and not lambda over 4 factorial. Okay. So let me just write it down. There are 4 factorial ways of picking creation and annihilation operators. That cancels this guy here.
That didn't come up in the Yukawa case because they were distinguishable.
Yeah, they were all distinct fields. So there was a psi dagger, and a phi. These things typically, well, they only come up when you have fields. There's another point that's similar to this, which is that when you're writing down diagrams in phi to the 4 theory, that this kind of fact that there's various choices about the way you do things raises its head again. Okay? It raises its head only for 1 loop diagrams and higher, but sometimes the diagram that you write down has to come with an extra factor of a half or a quarter or something like that. And there is some algorithm for figuring out when you do this and what's required. It's to do with the symmetry of the diagram, and these extra factors are called symmetry factors. So I'm not going to go through them here, but you should just be aware that this arises in the phi to the 4 theory, and we may set a homework exercise where you have to figure this out. If not tomorrow's tutorial, you'll have to go through and just see how this can arise. So all I'll say for now is just be aware that when you have things like phi to the 4, where the fields are not all different, there can be extra factors of 2 and 4 that arise in Feynman diagrams. Okay. You can read about this in Peskin and Schroeder if you're interested, and I'm sure one of the other lecturers will also comment on it, probably Peskin. Okay, any questions about this? I'm actually going to stop talking about interactions now. But what I do want to do is spend 5 or 10 minutes telling you what I'm not going to tell you, just so you kind of have a view about what I'm missing, and you know what you don't know, which is sort of half the battle, right? Knowing what you don't know. So then you can figure it out later. So let me mention 3 things that, if we had more time, if I had another lecture or two, I would go through. But because we're short of time, I'm not going to. And I think all of them you're going to see in other contexts. Okay, so let me just tell you about this. Okay, so things I'm not going to tell you. Okay. So number 1, and this is what you're going to do, was one of the things you're going to do in the tutorial session this afternoon. And it's a really nice physical question. It's the following. We've computed the amplitude for, let's say, nucleon-nucleon scattering in this scalar Yukawa theory. Tube size go to tube size. So you've got a formula for this. But it's not really clear what that formula is telling us. After all, since high school, we've had a way of explaining how particles interact. It's F equals ma. And it would be really nice to take this sort of fairly abstract formula we've got and translate it into something that we can plug into the F of F equals ma. Right? So really just make contact with standard physics. After all, it's sensible. We have 2 nucleons sitting here, and we make them go together slowly. If we're sort of a 19th century physicist or an early 20th century physicist, what do we see? We see them go in, and then they come out. Okay? And there should be a way to explain that trajectory in terms of the forces between the particles. Okay? So the calculation to do this afternoon in tutorials is to figure out what that is and to translate that amplitude into a force between particles. Or we're a little more sophisticated in forces, so we'll just have a non-relativistic potential that is the energy felt between the separation of the particles. Okay? So how do we do this? Well, what you have to do is make contact with the non-relativistic scattering calculations that you did in Malcolm's course. So you say the following. Pretend that there's the following potential energy between the 2 particles. What amplitude would I get if I scatter them, and then match that amplitude to the one we've computed here? Okay? So is that clear what we're going to do this afternoon? Let me tell you the answer, because it's interesting. Well, I've told you the answer. It's what's called a Yukawa potential. So the answer is that the potential between 2 particles, so this is the separation. So just, non-relativistic spatial separation between 2 particles. Sorry, that's not lambda. Ah, that is lambda. That's the right answer. Okay, so it's G over 2m. Remember, G had dimensions of mass. So G over m is the dimensionless quantity. And I told you that for things to be weakly coupled, G had to be much less than m. And now you can see explicitly that that's true, that would be a small number if that's the case. So a small force between the particles.
So usually these kind of 2 particles copy each other.
Yeah.
As another is kind of the advanced scattering operative, because that's what we do in classical electronics, right?
Yeah, good. So there's a slight change of perspective. So usually in classical quantum mechanics, you have some potential here, and you scatter a single particle in that beam. So the slight change of perspective is to consider two particles, but their relative separation is the dynamical variance, right? And that relative separation is moving in this potential.
Or can you consider a frame in which, like a reference frame? I know we're talking.
Yeah, you could probably, that's right. You could probably keep one fixed.
Okay.
Not really, actually. That would have to be a big heavy one, and this a light one. So when they're the same mass, it's best just to take the center of mass degree of freedom and throw it out. So what you're left with is a problem for a single dynamical variable separation.
And so that M is the mass of either one of the amplifiers.
Yeah, and I think that's exactly why there's two M there. It's because this is the reduced mass, or whatever it's called in classical mechanics. Other questions about this? Okay, so this is the kind of potential that Yukawa suggested back in the 1930s to be responsible for the strong force. And typically, whenever you have in quantum field theory, in 3+1 dimensions, two particles which are interacting by the exchange of a massive particle, the effective potential they feel is always of this form. So the 1/r is because we're in 3+1 dimensions, and it's just the usual Coulomb-type force. But now it's suppressed by this exponential fall-off, where the exponential gets small as soon as r gets bigger than 1 over the mass of the particle. Yeah.
Then take a potential and then try to find some quantum field theory for it.
There's various things you throw out to get to this. Not least the fact that you have to go to a non-relativistic limit. So if you start with a non-relativistic potential and you want to sort of bootstrap up to a relativistic field theory, I don't know if that's always possible.
We probably only included first order diagrams.
That's also certain.
Yeah. Is
One thing I want to stress, there's a minus here. Okay, what does that mean? It means that the potential is attractive, the force is attractive. These nucleons want to come together because of this exchange of the light. If we did the same calculation for nucleons and anti-nucleons, we'd find exactly the same answer. And this is something which is important to stress. It's worth sort of checking this afternoon when you go through this. That if you have forces that are due to the exchange of scalar particles, they're universally attractive. Likes attract and opposites attract. Here we're seeing that likes attract. Nucleon doesn't attract it. So there's a nice sort of chain here. Spin zero exchange always gives rise to attractive forces. Exchange of spin 1 particles is what we mean by electromagnetism, and we'll see this later in the course. And there, of course, opposites attract and likes repel. So there's a flip in this line. When you go up again to spin 2 particles, that's what we mean by gravity, and again, everything attracts. So spin 0 and spin 2, always attractive. Spin 1, attractive or repulsive, depending on whether you've got particles, the same type of particles.
Does it make sense to ask the same question for spin half particles?
Yeah, no, for the following reason, that 2 particles come along, and this guy spits out a spin half particle. What's left carrying along is no longer the same particle. It spins different by a half.
But if we exchange several spin half particles, or
oh, good. Yeah. So you can imagine box-type diagrams.
Yes.
I'm fairly sure, but diagrams of this type don't give rise to forces of this type. I think there's also sort of, I think things are just more subtle. There's spin-spin interactions that you have to take care of. I'm not quite remembering. We'll talk about calculations like this when we come to spin half particles. And even there, You know, even there, it's the case where this sometimes vanishes and then it's over the next term. I can't fully remember. It's too easy, but I think.
Do we associate a potential with spin-off particles? I mean, it's more like a potential implies a force, right? And the force-carrying particles are usually associated with bosons.
Right, but that's precisely because you know it changes. But you could consider a force due to this, and there should be a potential. But it may be that it's zero in the non-relativistic limit, or you know, I'm not sure.
Can you take extra diagrams somehow to come up with like relativistic corrections to Coulomb's law and this kind of thing for?
Yeah, absolutely.
Proton scattering off an electron. That's got an electron as the internal line, right? And can't you, isn't there potential for that? So isn't that just quantum stuff?
Well, you could do more interesting photon scattering of photons.
Right.
But I don't think you can write that in terms of, it's hard to make a photon non-relativistic. Okay, so that's the first thing I'm going to talk about. Okay, the next thing I'm not going to talk about is cross-sections and decay rates. So this has a similar flavor to the first thing I didn't talk about. It's that, you know, we've got these quantum amplitudes. Well, what we really want to know is how we're going to compare things we measure at the LHC. And there's a whole extra step there. Of course, you basically know what to do. You take a quantum amplitude, you want to know the probability, you square the complex amplitude. One square. So it's basically that step. But you know, there's a few little subtleties along the way. So I think a lot of these subtleties you dealt with in Malcolm's course already. But I'm not quite sure what he did, and it will take a lecture to go through this, and most of it might be repeated, so I'm just not going to mention it. I'm fairly sure that Michael Heskin will talk about this in the standard model, so you're not missing it. But I've written a few pages in the notes, so if you're interested. Finally, I know you'll come across this more in the next course. I'm not going to talk about correlation functions, which are also often known as Green's functions. So let me firstly just tell you what they are, and then I'll stop talking about them. You know, we developed machinery to compute scattering amplitudes in quantum field theory. So answering questions like, I have some particles here and some particles here, and I throw them together, and what's going to come out with what probability? So these are exactly the kind of questions that you need to ask for accelerators. But it's also clear that it's very much a setup which is oriented towards high energy particles. And there's lots of other things you could do with quantum field theories where the questions you want to ask have nothing to do with scattering, at least not obviously. For example, you may come up with a brilliant idea for what happened during inflation in the early universe based on some quantum field theory. And if you came up with this idea, you want to know if it was right. And the thing to check against is the microwave background radiation. And in particular, the spectrum of density perturbations over the sky. If you want to do that, you have to know how temperature there is correlated with temperature at a different point in the sky. Now, it's not at all clear what you should calculate in terms of scattering amplitudes. What you need is something more abstract, which is called a correlation function. So a correlation function, also known as Green's functions, they're sometimes known as endpoint Green's functions, are the following. Okay, so again, it's a time-ordered product, but it's objects in the Heisenberg picture, now not the interaction picture. And this guy here is the vacuum of the true theory. That's a somewhat different object from what we've been calling zero, which was the vacuum of the free theory. Okay? So what I'm not going to tell you about is how you compute things like this in terms of Feynman diagrams. Again, it's all in the notes if you want to go through it. And it's fairly nice. You know, there's nice ways in which this gets changed into the other vacuum that we've been considering. But basically, this is related to the other vacuum by considering all bubble diagrams. So bubble diagrams are things like this. You know, anything that's Feynman diagram you can draw with no external legs. So this is somehow the true vacuum here. And there's very simple ways to compute this. It's really not a hard object to compute using Feynman diagrams. This will be discussed in the next course on quantum field theory, but like I said, it's also in the notes. So typically what one wants to compute in quantum field theory are not so much scattering amplitudes, but correlation functions of this type. Yeah?
The u-value function.
Is a
The u function.
sorry,
It's u-value.
real value.
Yeah.
In this case, yes, if I had complex scalar fields. No, I think it's a quantum amplitude, so I think it's always, well, in this case, yes, because these are Hermitian operators, but in general, not necessarily. No, even if these are Hermitian operators, then it's a complex argument. Okay, so I've sort of just flagged these things up so that you're aware that there's other things out there to learn and hopefully make contact from this later. Oh, by the way, some of these issues about the bubble diagrams we'll do in the tutorials and understand how these things are placed.
I don't know if you want to go into it, but the correlation functions here. Like if you just have a two-point correlation function, it appears to be phase dependent, and even worse, it
appears to be what dependent?
Frame dependent, and even worse, it's not just like smoothly frame dependent, but it appears to have a discontinuity when the time ordering of the 2 points changes.
No, these things will be fully Lorentz covariant.
Okay.
Yeah, in the Heisenberg picture, these things should be fine.
Even despite the time ordering, or because of the time ordering?
The time ordering is actually a relativistic
Okay.
thing that we can Peskin choose that.
Okay.
These should be covariant. By the way, you asked a question earlier, which I said I would duck. And I have ducked it, but I don't remember what the question was.
Goodness. Oh, right. When you're, so you integrate, so when you calculate the scattering amplitude for like, well, pretty much anything you showed, you get a delta function on the momenta, and then you sort of, like that shows up in front of every amplitude. So,
oh, good. Thanks. Yeah, I was going to duck it at this point.
Yeah.
Good. So what happens? You take the amplitudes and you square them to get the probability. But now you've got a delta function squared. Right, so the amplitude comes with a single delta function, sum of the momenta.
I would think that you would, because remember the states you have on either side are not real. Like if you have momentum eigenstates on either side, and those aren't real states. So you'd have to.
So there's a few different ways to do this. If you just take this, which is equal to I times a delta function, and you square this, you get a delta function squared.
Yeah.
But one of these delta functions is an honest delta function, which is telling you momentum is conserved. The other one is basically delta of 0, which you interpret as the volume of space. So you divide that over here to calculate some probability density. So That's the question I was going to dodge, but that wasn't quite your question.
No.
So your question is that these plane wave states are not normalizable. They're
No,
not
well,
normalizable.
I'm just saying, like, you don't. It seems like you don't have to play with delta functions at all. Like,
You
because the left hand.
could, of course, just
Yeah.
smear this over a wave
Right.
packet, just like your quantum mechanics, and then.
So is it accurate to say that the left-hand side of the sentence makes sense if and only if the right-hand side makes sense?
I think it's accurate to say that delta functions make sense.
Well,
And we should just.
but you don't need them. They're totally
You don't
irrelevant.
need them, but if you want to do without them, you'll have your work cut out for you.
Do you? I mean, you can. It seems like everything here could be done
You
with.
could smear this with a wave packet, but
Yeah.
you end up with a wave packet here.
Yeah. Which is what you
It's
really
easiest
have.
just to
right?
do this at the end. You know, whatever you want to do is fine. But, you know, the equations that we write down here are typically long and tedious, and when you do calculations, they fill many pages. And you want to find the way to use as less ink as possible to make as few mistakes as possible. Okay, so that's me done for interactions. Are there any more questions? But by the way, the reason I'm not going to dwell on this, we could spend many more courses talking about aspects of interaction. But the real point of this course is to sort of give you the basic ingredients of quantum field theory. And so what we have left to do is to understand spin half fields and spin one fields. And they all come with their own substances. But basically what we're going to do now is introduce those and explain everything we've done so far for scalar fields. Okay, so let's move on. We're going to talk about spin half fields, which are described by the Dirac equation. So this is section 4, Dirac equation. Okay, so I'm going to go kind of slowly. I know Malcolm did the Dirac equation already, but this is one situation where nobody else is going to do it, and I think it's worth just going very, very slowly and building up to it. And so not just writing it down, but seeing why this is the miraculous equation that it is. So I think we won't get to the Dirac equation until the end of tomorrow's lecture, but we're going to understand the Lorentz group a little bit and figure out why this is such an interesting and beautiful equation. Okay. So yeah, so far we've only considered scalar fields. And under a Lorentz transformation, basically what happens is under an active Lorentz transformation, the field just sort of rotates or boosts, and the new field is the old field evaluated at the point in space where you were before you did the active transformation. Okay? That's that lambda to the minus 1 there. But, of course, the fundamental particles that we know of aren't described by scalar fields. In fact, we haven't discovered yet a single fundamental particle which is described by scalar fields. Hopefully this will change in the next 2 years, but at the moment, everything that we know of that we believe is fundamental has an extra property which is a little intrinsic angular momentum that we call spin.
Which particle were you meaning that you were?
The Higgs.
Oh, that's scalar.
The Higgs, oh, sorry, yeah. I should stress this. The Higgs is a scalar particle.
Oh.
So in the standard model, the Higgs is the only scalar particle. Okay? Sorry, I should have stressed that. Okay. So this gives rise to spin 0 particles. So to describe fields with spin, to describe particles with spin, which means the particle has some intrinsic angular momentum. What we're going to do is look at fields which themselves have some non-trivial transformation under the Lorentz group. Okay, so what do I mean by a trivial transformation? By trivial, this is changing because the space is changing, but the components of the field aren't doing anything special, and that's because there's just one component and it can't really do anything. So an example of a non-trivial transformation that you know already is the gauge field of electromagnetism. Okay, so the spatial part changes, the argument changes as for a scalar field. But now, of course, when you do, say, a rotation, the the electric field in the x-axis rotates into the electric field in the y-axis. So that's what this guy here is telling us. Okay, so you might think that the simplest thing to do is now to consider this because it's very familiar, but it turns out that quantizing this comes with some pretty interesting and difficult subtleties that we'll get to next week. So instead, it's best to look at the next one up. So we started with spin 0. It's best to look for a spin half. Okay. So what I want to do is try and tell you what a spin half field is and how it transforms under the Lorentz group. Okay, so in general, a field can transform in the following way. So you have a whole collection of fields, and they're labeled by some index A that runs from 1 to some unknown number. And under a Lorentz transformation, this set of fields could themselves transform into each other in some way. The way they transform into each other should be a matrix. The matrix should depend on which particular Lorentz transformation you're doing, and it should have certain properties. And these properties are such that mathematically we would say that it's a representation of the Lorentz group. Okay, so what does it mean that it's a representation of the Lorentz group? Well, basically, it just reflects all the multiplication properties of Lorentz transformations. Couldn't we have a projective representation? I don't think so, but Sorry, say again?
Yeah. There's a lot of.
Are there projective representations of the Lorentz group?
Oh,
They may not
Lorentz
be-
group.
They may all be trivial.
Okay.
Yeah, I don't think
Okay. No.
there are any, but I'm not. Certainly, they don't arise in physics that I come across. The representations have been classified.
I'm sorry. We're asking. We're not. So not doing the representation of the smaller, like SL2, like of the rotation group, but of the whole. Oh, of the Lorentz group. Yes. Okay. So what happens, I believe, is that. So you could have you could need a projective representation of a Lorentz group, but there's some way in which, so SL2C is a double covering of the Lorentz group, and there's some way in which like any projective representation of the Lorentz group comes from an ordinary representation of SL2C. So what you're actually doing is finding representations, ordinary representations of SL2C. And when you do the Poincare group, it's similar. The Poincare group is the product of the Minkowski translation group with Lorentz group, the semi-direct products. And you like
Let's move on. I think maybe, but nobody knows is the answer.
The answer is no.
Okay.
Projective representation of using SL2C.
So how do we figure out, oh, I should say a bit more about representations. So what are we capturing here? We're capturing, the fact that the Lorentz group is a group. A group means I can do one thing, and then I can do another thing, and that's still a Lorentz transformation. And so, by the way, how many have seen representation theory how many haven't seen representation theory of groups? Good, so enough that I need to just spell this out. So there's a structure to Lorentz transformations, which is exactly what I said. It's this thing called a group structure, but it basically means you do one thing and then you do another thing, and that's the same as sort of doing the whole thing in one go. It's a very obvious structure, right? I can rotate this way and rotate this way, and there's one rotation which would take me to that original situation. So what I've got here is the fact that I want some matrices D, which basically have the same properties as the standard matrices lambda that we have to describe Lorentz transformations. So in particular, for every lambda, I want to associate a D. But if I take two Lorentz transformations in a row, lambda 1, lambda 2, there's a matrix D associated to that, which is equal to taking the matrix associated to lambda 1 and multiplying it by the matrix associated to lambda 2. Okay. Similarly here, the inverse of D is D of the inverse Lorentz transformation. And then there's this trivial one that D of, if you don't do a Lorentz transformation, then D is also 1.
Is this necessary? Like, you'd think with the first two axioms, this third one's not
Yeah,
necessary.
you could well be. Good, so what we want is to find all possible Ds such that this is true. That's what's meant by finding all representations of Lorentz. Okay, so how do we go about finding this? And this is true for any, these things are called Lie groups, like continuous groups that depend on a continuous number rather than just a discrete transformation. They're called Lie groups. And there's a standard technology to understand the representations of all Lie groups. I'm not sure, is there going to be a course on this? Okay, good. So there's a standard technology to understand the representations of all Lie groups, which is to look at what happens when you make just infinitesimal transformations. Okay? So this should hopefully be slightly familiar from angular momentum in quantum mechanics, where angular momentum is associated to rotations, but what you do is you consider making just infinitesimal rotations, and you get operators which obey certain commutation relations that are responsible for these. Okay. So to find representations, and again, this is true of any group, is we look at what's called the Lie algebra. What this means is we look at infinitesimal transformations. Okay, so what's an infinitesimal transformation? We take a Lorentz transformation which does nothing, and then something which is small, and by small we mean it's of order epsilon. Okay, so these Lorentz transformations are special. They have particular properties. The properties of the Lorentz transformations are going to be imposed on the properties of these infinitesimal transformations. Okay, so let's see what that is. Okay, this is the definition of a Lorentz transformation. We saw this at the very beginning of the course. It's Lorentz transformation transpose times Lorentz transformation equals unit matrix, but where unit matrix now has a minus sign because it's the Minkowski. Let's plug this into here. Okay, it's very clear. So what have we got? We have the deltas, which are just going to give back this, and then there's the terms linear in epsilon, which are going to be the things that are interesting, and there's the term epsilon squared, which we're going to neglect. Okay. So what this means is that looking at the terms linear in epsilon, okay? Okay, so this is very simple. We have these Lorentz transformations. If we do an infinitesimal Lorentz transformation, the matrix that we have has to be very special. How is it special? Well, it has to be antisymmetric. Okay. Notice that I've raised both the indices here, and it's actually only antisymmetric when both indices are up. Okay.
I think the mu in epsilon mu tau.
Mu?
Or epsilon omega mu. Yeah, over 3 terms. I think you've got.
Oh, yeah, that's right. So one of these, this should be a nu. Is that right? Yeah, that's right. Good, thanks. Okay, so what we want for infinitesimal Lorentz transformations are antisymmetric matrices. So these are 4 by 4 matrices. How many antisymmetric matrices are there? Well, there's 4 times 3 divided by 2, which is 6 possible matrices. And this is exactly what we wanted because the Lorentz transformations consist of 3 rotations and 3 boosts. Okay, so people happy so far? Infinitesimal Lorentz transformations correspond to antisymmetric matrices. So what we're going to do now is introduce a basis of infinitesimal Lorentz transformations. That is that any antisymmetric matrix is going to be a linear combination of 6 antisymmetric matrices that we choose and which I'll now write down. So we'll introduce a basis of 6, 4 by 4 antisymmetric matrices. Okay, so I need to explain the notation here. This is the 4x4 matrix labels. Maybe matrix labels is the row column labels of the matrix. Now this is a label that I could have written as, say, capital A that went from 1 to 6. So this is the label that's going to tell me which of the 6 matrices I've picked. But rather than have a capital A that goes from 1 to 6, I've chosen a rho and a sigma, each of which go from 1 to 4, actually 0 to 3. But it's anti-symmetric in rho and sigma, which you can see here, that say rho is 1 and sigma is 2, I get a 1, 2, and a 2, 1. But that's exactly the same matrix up to a minus sign as 2, 1. Okay? So this labels which of the 6 matrices I'm interested in. Maybe I'll give some examples, and then that will clarify any confusion. So for example, so in particular, there's no m here which is 0, 0, or 1, 1, or 2, 2. The only m's that we have are 0, 1, 0, 2, 0, 3, 1, 2, 1, 3, and 2, 3. So there's 6. Okay, so here's 2 examples of the matrices. All I've done is I've picked 0 and 1. I've plugged it into here. I've plugged it into here, and I've figured out which elements are non-zero. Okay, so this is an infinitesimal boost in the x direction. Okay, 0 is time, 1 is x. So this is basically a Lorentz transformation, infinitesimal Lorentz transformation, which is a boost in the x direction. This, meanwhile, is an infinitesimal rotation around the z direction. Yeah. Yeah, exactly. So it's a little bit odd. I've told you I've written down a basis of 6 antisymmetric matrices. I gave you an example, and it's not antisymmetric. So why is this? It's because, as was just pointed out, the nu index sits at the bottom as I've written it. If I was to raise it so there was a mu and a nu, I'd pick up a minus sign here, and it would be antisymmetric. Okay? But as it stands, I'll leave 1 up and 1 down. Tibra.
Also, just to clarify, these are the generators of the boost, infinitesimal boost, right? So every add is one.
Oh, good. Yeah. So thanks. So I guess I didn't want to say those words because people hadn't seen representations, but there are people that have seen representations, so I'll say those words. Yeah, this is the Lie algebra element, or the generator of the boost. What that means is that the actual Lorentz transformation, as we've seen, is 1 plus a little small number times this matrix. Okay, so that's what we mean by a generator.
Well, that answers the next question.
Good. Okay, so as I said, I've now got a basis of these guys. So we can write any infinitesimal Lorentz transformation, or the generator of infinitesimal Lorentz transformations, as a linear combination of these 6. Okay, so now come the final two statements of the lecture, and these are going to be the things that you're going to have to take on authority if you haven't seen representations of Lie groups before, because I'm not going to be able to prove these in this lecture. So hopefully they won't be totally unfamiliar. So the first one is that any finite, and actually there's a caveat to the any, but I'll come to that later, Lorentz transformation can be written by taking this infinitesimal one and exponentiating it. Okay, so let me just explain the notation before I try and explain what's going on here. This is a 4x4 matrix, the M, but I've not included those 4x4 indices. Okay, so there's a mu and a nu index, which is floating around here and here, which I've just left off, hopefully for clarity. Okay, so this is a 4x4 matrix. This is a set of six 4x4 matrices, and this is a set of 6 numbers. So this whole thing is a given 4x4 matrix. And then I exponentiate the 4x4 matrix. Okay? What do I get if I do that? Well, if these are very small numbers, I get the 1 plus the small infinitesimal piece plus higher order terms. Okay? So what you need to know about Lie groups is that any element of the group can always be written in this exponentiated form, where there's the element of what's called the Lie algebra that sits here. So for those who haven't seen Lie groups, this may be the tricky thing to understand. Okay? But any Lorentz transformation can be written in this form. So again, what are these? These are 6 numbers that tell me exactly what Lorentz transformation I'm doing. They're the numbers that say, I'm rotating by 30 degrees, or I'm running at 100 miles an hour in this direction. Okay? And these are the 6 matrices that are implementing that. Yeah, please.
The 6 numbers, how are they?
Yeah, they have 2 indices, but they're anti-symmetric because they're contracted with this, and the definition of this was anti-symmetric. Yeah, I probably should have written this on the board, but if you just look at the definition I gave, it's anti-symmetric. So it looks like there's 16 numbers, but because they're it looks like there's 16 possibilities, but because it's anti-symmetric, there's actually just 6.
What's the matrix? Do you know the left?
It's exactly the same, because anything that's, so suppose that I write down an omega 1, 1. That contracts with n11, but there is no n11 and 0. So the only thing that's contributing here is omega 1, 2, and that's contributing in the same way as omega 2, 1. So there's really just 6 of these guys. Okay, and there's one final thing you need to know, which is the Lie algebra. So the generators oh, but by the way, this any isn't quite right. Strictly speaking, these are Lorentz transformations that are connected to the identity. So there's some like just flipping, well, doing a parity transformation, doing a reflection, which you can't get by this way. So you have to add an extra couple of operations to get the full Lorentz group. We'll come to that later.
What does the word finite, I forgot to ask this earlier, what does the word finite?
I just mean in contrast to infinitesimal. So this is the finite rotation.
Yeah.
And this is an infinitesimal. Okay. So finally, the Lie algebra is the following. So you can figure this out just by plugging in the definition of the M's important equation, so let me just box it all. Okay, so again, just to stress, this is a 4x4 matrix, and I'm commuting it with the 4x4 matrix, but I'm dropping the new labels because there's already enough labels in this equation. But each of these is a 4x4 matrix where the row column labels have been left implicit. Okay, so let me just repeat what we've done here. We consider Lorentz transformations, and I've either reminded you or told you that all Lorentz transformations can be written by picking a bunch of numbers which tell you which one you're doing, but basically taking a linear combination of 6 matrices. Okay, these are the 6 possible infinitesimal 3 rotations and 3 boosts. Okay. These 6 matrices have particular commutation relations amongst them. This is how they commute. So each of these is just a constant matrix. It looks abstract, but it's not. And these actually are 1s and 0s in these matrices. The key step is that this equation here encapsulates all that's important about the Lorentz group. Okay? In particular, if you can find some other matrices that aren't the ones I wrote down with 1s and 0s, that obey these same commutation relations amongst them, you take these new matrices, you put them here, and you're guaranteed to have a new representation of the Lorentz group. Okay? So this might be familiar from rotations. Remember, you have sort of what I call finite rotations, where you actually do something. But when you come to quantum mechanics, the way you encapsulate rotations are in the SU2 commutation relations. That rotation of x commutator rotation of y is I times rotation of z. Okay? That's what you start looking at. You should think of these in exactly the same way as those SU2 commutation relations. So whenever we look for representations of Lie groups, what we really do is try to find new matrices that obey these algebra, this Lie algebra equation, and then we take those matrices and we throw them in an exponential, and that gives us a representation of the group. So in the next lecture, we're going to find new matrices that obey this relationship, and that's going to give us new representations of the Lorentz group. Is that clear to people? Yeah? Any questions? No? All good? Okay, coffee.